Hi everyone. I was making my omelette for breakfast this morning. I always use 4 eggs, but then I was reading in the newspaper that 1 in 4 eggs can potentially have salmonella in it. So from tomorrow, I'm only going to make my omelette with 3 eggs. I hope you appreciate the humour there, and disclaimer, that story is not true. Alright, so today we're talking about probability, and when it comes to probability, we can describe the chance of something happening either with descriptive words like it's likely, it's unlikely, it's certain, it's impossible, or we can use numbers, a bit like in that story about the salmonella where we might say 1 in 4 or 1 in 5, and what we're really saying there are fractions. So fractions, decimals and percentages are the things that we use to describe the chance of something happening with numbers. So you can think of it a bit like this. We have a sort of a zone of possibility. Down this end would be 0%, and up this end would be 100%. And so if something has a 0% chance of happening, then we would say that is impossible. For example, being a Collingwood supporter and being classy, that would be impossible. Up here at the other end, we have 100%, and so these things are certain to happen, just like Melbourne winning the premiership this year, that would be certain, so that would be 100%. And then in the middle, we've got everything else. So obviously right in the middle, we have 50%, and so we say that if something is 50%, then it is even, which means it has just as much chance of happening as not happening. And so the rest of these zones are sort of filled in. So we'll say things sort of up in this area are very likely. Things down in this sort of range are still likely because they're more than 50%, but not as likely as things up there. And then obviously down here, we have things which are very unlikely and unlikely. So let me give you a few scenarios and see if you can think about where they fit on that line. So the first one is seeing a Tasmanian tiger. Where does that fit, do you think, on that spectrum? 2 types of people here. Some people will say it's impossible, Tasmanian tiger is extinct. Other people will say, oh, could still be one out there. So I would say it's very unlikely. We can't prove it necessarily, so that's a bit of a subjective one. You can make up your mind. What are the chances that when they reduce the restrictions in Woolworths and Coles, people are going to start stockpiling toilet paper again? Would you say that's certain to happen? Very likely? Likely? What do you think? All right, there's some sort of thought-provoking ones. On a day-to-day basis, though, we do make probability decisions all the time. And if we go back to the supermarket again, you've filled up your trolley, and then you do a scan, don't you, to see which aisle you think is going to be the fastest moving aisle. What is my best chance of getting out of here quickly? And so you scan the aisles and you make a probability assessment, don't you? Aisle 3 looks pretty unlikely, that guy's got a big trolley. Aisle 2 is looking good, not many people there, seems to be moving quickly. And so you're making that sort of decision when you're picking what aisle to go in. If you're a surfer, then you also make decisions like this when you're looking at the weather forecast, when you're looking at the wave forecast, thinking, where is my best chance of getting that big wave? So we make decisions like this every day, not with the actual maths and numbers, but we go through that probability assessment in our heads. And then, of course, there are things which rely very heavily on probability and have a big impact on people's life. And so the governments will do these sorts of things all the time, but obviously with numbers, with more, we call it quantifiable data. So that's data with numbers that they can actually calculate and use to make decisions. And so the coronavirus is an example of that at the moment. governments are doing probability calculations on, how many people is this going to affect, and then how is that going to affect incomes, how is that going to affect our health system. All of those sorts of things come back to probability. If one person gets infected, what are the probability, what is the chance that they will infect other people? And so there are different calculations they do. And that's really important information to have for governments when they set these restrictions for us. We've been really lucky in Australia. We've been able to manage that curve and keep it nice and low, which has meant our health system has been able to cope with the infections we've had so far. But overseas, other countries have struggled. And so in some countries where their health systems are just overwhelmed with sick people, they have to make really serious and really ugly probability decisions. Let's say they only had 3 ventilators available, but they've got 10 people who need them. How do they decide who to give those to, knowing that those other 7 people will likely die without that ventilator? And so they're making probability decisions based on who they think is most likely to benefit from it, who they think is most likely to be able to, go on and work and live after that and sort of, contribute to society, those sorts of decisions, which are really tough decisions to make because you've got people's lives in your hands. And so we've got this whole spectrum where probability is involved, from picking an aisle at the supermarket to who do we keep alive and who do we let, battle the virus on their own. So be thinking about this as we go through the unit on probability. Be thinking about the descriptive language, but also the numbers. Now we said that we can use percentages, we can also use fractions, and so I'll change the colours here. So 50% would be 50 over 100, and 100 would just be 100 over 100. So that's fractions. We can also use decimals, and so for decimals, 1.0 means that something is certain, whereas oops, that was a good one. 0.5 is the decimal for half. And obviously you've got all the other numbers in between, 0.7, 0.8, 0.81, and so on. All right, so I just want to talk to you now about how to calculate the probability, how to calculate the chance of something happening. So we're going to put a little heading here, calculating probability. And there are 2 main pathways we take when we want to calculate the chance of something happening. It depends on whether we can calculate it just from a theoretical perspective, or sometimes we'll actually need to do an experiment to get the data that we need to make that calculation. So over here, we're going to have theory, and over here, we're going to have estimate. And just in brackets, I'm going to put relative frequency. That's something we'll come back to in a minute. All right. So we've got these 2 pathways. So if we have something where we can calculate it theoretically, then we're going to follow this pathway. And there are certain formulas that we use to calculate something theoretically. So Diazepam. Some of you are familiar with this already. It's got a range of different exercise activities on it. And so there are 6 faces on this dice. And so what I'm going to do is make a bet with you that if I pick one and roll it and get it right, then you have to do 10 of whatever that is. But if I roll it and get it wrong, then I have to do it. So I'm going to pick burpees because I don't want to do burpees. So if I get it right, then you have to do it. So there's burpees. And so the probability of me rolling burpees, how do we work that out? Well, there's 6 faces, and one of those faces is burpees. So when I roll it, I have a 1 in 6 chance, don't I? There's 1 chance out of 6 possible outcomes of getting it. So when we think about that theoretically, so we're going to say the probability of success, and this is how we write it with maths notation, so that P means probability of whatever is in the brackets. The probability of success, which in this case is burpees, equals the number, and that's just an abbreviation for the word number. NO dot means number. So number of successful outcomes over the number of total outcomes. So in this case for burpees, we would have 1 divided by 6. We have 1 successful outcome divided by 6 possible outcomes. So that's how we get the 1 in 6. And on the flip side of that, the probability of not getting burpees, the probability of not success, equals 1 minus the probability of success. I hope that makes sense. So what we're just saying is, we can think about if the probability of burpees is 1 in 6, then the probability of not getting burpees is everything else in our spectrum to get us back up to 1. So if we start with 1 being the certainty that we're either going to get burpees or we're going to get something else, then if we take away the probability of burpees, then we're left with the probability of everything else. And so that would be 5/6. If it's 1 out of 6 chance of getting burpees, then there are 5 out of 6 chances of not getting burpees. So we just flip it around, and we do that by going 1 minus the answer. Over this side, these are our estimates. And so to do an estimation, you actually have to go and do an experiment to get that data, because we don't have the theory of it. And an example is me in my office throwing paper into the bin. So when I'm finished with my paper, obviously not wasting good paper, throw it into the bin. What are the chances of me getting that paper into the bin from my chair? We don't know. It's not like you can look it up in a textbook. I'd need to actually do an experiment. And so I did. Here's how I went.
Off the rim. Got it.
So as you can see, not great. I was actually expecting to do better than that, so I'm going to have to work on my form there. But what we do with that information now is we calculate what's called the relative frequency. So I'm just going to abbreviate that here, relative frequency. And the way that we calculate it is we go the number of successful trials divided by the number of total trials. So in that experiment that I did, I got 1 out of 5 shots in. So 1 successful trial out of 5 total trials. So that means the relative frequency of my aim is 1 in 5. And we could convert that to a decimal, which would be 20%, or we could write it as 0.2. Now there's a bit of a convention in probability that for estimates, we use percentages or decimals, whereas for theory, we use exact fractions. So coming back to our theory, we said that the probability of getting burpees was 1 in 6, and probability of not getting burpees was 5 in 6, and so we would leave those as fractions. We'll do one last step now to finish off our calculation depending on which pathway we've taken, and that is to work out the expected frequency. And so the expected frequency is then what we're expecting to happen on a larger scale. So, for example, I had those shots into the bin in my office. If I was to do that 100 times, how many times would you expect me to get it in based on my form in that original experiment? So if I'm getting it in 20% of the time, then after 100 shots, I should be able to get it in 20 times. That's the theory. Now, it's probably going to be slightly more or slightly less, isn't it? It's not going to be exactly 20, just like we know the theory of flipping a coin is half, so 50-50, but if you flipped a coin 100 times, you're not necessarily going to get 50 heads exactly as your result. So you know it should be close to 50, but it might be a bit more and a bit less. But the way we calculate expected frequency, and I'm just going to abbreviate here expected frequency, so EF equals the probability of success times the number of trials. Or if we've done an estimate, then instead of the probability of success, we would use relative frequency instead. So relative frequency times the number of trials. And so that's how we calculate probability. Start by thinking what it is you're trying to work out. Is it theory? Is it an estimate? You follow the pathway, and then when you come to working that out on a larger scale, you just need to use that probability that you found and multiply it by how many times it's going to happen. And this is used in all sorts of industries, but one example is football. So when you're watching the football, often you'll see someone lining up ready to kick the goal, and they'll be in a certain position. Remember, the football ovals they're ovals, they're curved, and so they might be on the side trying to kick towards the goals. And so on the screen, the TV operator, Channel 7, whoever is operating it, will put up a bit of data showing that they've kicked 10 goals from that same position, that same spot on the ground this year. But that 10 goals came from 30 kicks. So they got 10 goals out of 30 kicks. And so they use that to predict, okay, they're going to kick this goal from here now. And while that, in one sense, to us, just gives us a bit of, sitting on the couch at home and go, oh yeah, they're going to get it, or no, they're not. But for people in the AFL industry, that's a multi-billion-dollar industry. And so they use that as part of their strategies with their coaching. We want to make sure if this guy gets the ball, we want to make sure he's out wide on the wing. We don't want him to be directly in front of the goals because he's got a good chance of kicking it from there. Push him out wide, so if he does get the ball, his chance of getting a goal is less. And so that comes into their strategy and all the money that goes through that industry. So in one sense, it's just a game, but in another sense, it's more than a game. That's a playback to the footy show, but that's probably before your time. All right, I think that's it for today. Thanks. Burpees! Off you go.